I'll share my screen. We didn't have much left to discuss in this lecture, by the way. So I'm going to very quickly go over what we covered. We discussed the key concept of phase change memory. We discussed that you change a material from crystalline to amorphous states, and in a crystalline state, it has low resistance. Amorphous state, it has high resistance, and that's how you represent logic 1 and 0. We discussed the basic structure, which is usually made of germanium, antimony, telluride, GST, but there are other materials available as well. By the way, this is the region that changes from amorphous to crystalline, and this is a heater. So you use a really nice, well-structured, well-thought-of structure to heat up this material so that it can melt or restructure into crystalline form. Then we discussed some quick history. Notice that this concept dates back to 1960s, but then it stopped because of technology irrelevance. But then as we went ahead with nanotechnology, all on a sudden, the same concept makes sense because it takes much less energy to convert a material from crystalline to amorphous on chip now, because the amount of heat necessary to melt something is proportional to the volume. So when you go for nanotechnology, you reduce the volume in 3 dimensions, X, Y, and Z, and everything is being reduced by orders of magnitude. Okay, so all on a sudden, it started making sense. We also went over the brief story. We noticed that back in 1966, we had some activity, but then there was almost nothing. But then early 2000s or so, we started having a surge in interest in PCM, right? We noticed that, and because of nanotechnology, nothing else. We also discussed the type of chemical properties that are looked at when we explore this type of materials. Again, I didn't go into the details of the chemistry because we don't do that per se. Material scientists get into the depths of how did you know that germanium, antimony, and tellurium, when you mix and match them and make alloys, will be the best candidate? They were not the only elements that they studied with, as you can imagine. They studied many other systems and arrived at a conclusion that this combination is like a magic combination. Okay, that's how they arrived at it. And then we noticed, we looked at the ternary diagrams as to how, when you mix this in different proportions, you get different properties. But they're all more or less phase changing, but some have some beneficial characteristics than the other. So if you need higher set voltage or higher reset voltage, you go in one direction. If you need lower melting temperature, you go in the other direction. So people do experiments all the time with this type of ternary systems to further optimize the system. And it's not all random, by the way. They're trying to make sense of what needs to be done to improve it in which direction. What I mean by that is, say, if you keep increasing your antimony, it's not going to improve everything. It's probably going to improve something. So depending on your design requirement, people go in one direction or the other. And people try to study as to which direction we need to go to achieve what. So they try to tabulate them and make constants out of them. We also discussed the complexity of modeling this system because there are 3 different things coupled together: electrical IV, current voltage properties. And then we have a thermal system because temperature gives rise to, the structural dynamics. The structure changes, the crystal changes, that eventually changes the resistance. And that resistance change gives changes in the current voltage characteristics as well. So there are 3 different modules lumped together. So that's why modeling this system is more complicated than any other memories that we have seen so far. Everything else has a properly straightforward dependence on a physical phenomena. But here, there are 3 complicated things connected together. Then we also discussed the high-level process of switching from amorphous to crystalline. In one case, you use a current pulse, but it's a very sharp current pulse. So you increase the current quite rapidly, which increases the temperature rapidly and takes it beyond the melting temperature. So you melt it quickly and you don't give it enough time to cool down. So you basically fast quench it. You reduce the current. That means it reduces the temperature. So you melt it really fast and you let it cool really fast. So that means it doesn't get time to reorganize and create a crystal. It becomes amorphous. Okay. But for the other one, for amorphous case, you basically increase the temperature, but you don't melt it again. You don't have to melt it again. You take it above the crystalline temperature, which allows the atoms to move and vibrate, but not just makes it a liquid, for example. Okay. And then you give it enough time to reorganize. And the atoms reorganize themselves and then create a really nice crystal structure once again. That's the process. And see, this is a really strange way to represent the switching, by the way. No other memories use this type of argument of temperature-driven switching, right? So that's why it's unique for sure. Okay. And we also discussed that array structure, which is similar to everything else we have seen so far. You have your memory element and you have a transistor used as a selector. And you have word line, bit line, source line. It resembles the STTM RAM or many other memories that you've seen, resistive RAM, right? Memristors, they use the same thing essentially. As long as you have a 2-terminal memory like this one, you could always use a transistor in series and use the same array structure. I mean, don't change it if you don't have to. That's the thing. All right, so we just discussed this. All right, we also, these are all past things that we already discussed. I remembered, right? Remember the negative differential resistance that we discussed? So in phase change memory, when you switch from, this was the experimental data. When you switch from high resistance to lower resistance, there is a voltage redistribution that occurs between the load and the phase change memory cell. And the load is nothing but the transistor resistance, for example. Okay. And because of that, you have a snapback or negative differential resistance that shows up. This is an interesting signature of phase change memory when you observe the experimental data. So this is an experimental data. Notice the NDR here. Okay. We also discussed this in detail. So I'm just being a superficial discussion here. Next, we also looked at the device sample and as to where. Notice this is where the GST is, and these are your transistors. This is FEOL, front end of the line. So you make them first, and then you make the others next. They are at the back end of the line. And I also use this analogy of having a production line. You make the transistors first. That's why they're at the front end. And then you gradually keep making the top layer and top layer. And the phase change memory and other most fancy devices are made at the top layer like this. So that's why they're at the back end of the production line. That's why BEOL. I hope you remember these discussions, right? Okay, then this is new. This is definitely new. So we will spend time to discuss this properly, all right? So multi-level resistance. Good thing is by now you hopefully know the use case for a multiple level in a memory cell. If you have 4 different resistance levels, you could use them to represent, remember, 0, 0, 0, 1, 1, 0, 1, 1. 2 bits at a time instead of 1 bit at a time. If you have, imagine, okay, if you have 5 different resistance levels, will that be even more beneficial, folks, than the 4-bit? Let me ask the question again. Imagine a device gives you 4 different resistance levels. R1, R2, R3, R4. Is that beneficial for memory? Because you could represent 4 combinations. That means 2 bits at a time. But if a device gives you 5 different resistance levels, R5 as well, will it be even more beneficial or not? Why? No. The thing is, the next step is 8. Because to store 3 bits at a time, you need 8 combinations. So 5 or 6 or 7 will not help you unless you get to 8 again. And what's the next one? 16 and 32. Yes. Yeah, but the resolution between resistances yes. So I'm assuming an ideal situation that resolution remains the same. Given that situation, the more levels you have, the better it is, but not just any number. You need a certain amount of threshold to cross. So at the very least, people look for 4 different levels so that they could store 2 bits at least at a time. Okay. So it turns out phase change memory gives you a nice way to do so. Let me explain how. Notice this is called the mushroom cloud because it looks like a mushroom. This is the heater, and this entire thing is your GST material. Okay. When you pump in current, it brings heat and it melts the material and changes it into amorphous or crystalline depending on how you do it. Okay. But it doesn't occur throughout the material. It occurs like an umbrella, because that's how heat is dispersed. Heat is diffused like an umbrella in a semi-spherical form. I guess all good so far. So the more heat you provide, the farther spread out this sphere becomes. So by controlling the current level from being really high to medium to even higher, you could switch a small portion to a bigger portion. And by doing so, you could change the resistance levels. Does that make sense? And interestingly, for phase change memory, you don't have to do it in 4 steps. You could do it gradually, like really nice analog fashion. Instead of just saying we have 4 levels, we have many levels. Are you guys all good with me so far? Okay. What it alludes to is a synaptic behavior. And what does that mean? In our brain, we have neurons, and neurons are connected with each other. And at the connection point, the way we understand the brain operation is at the point of connection, we have synapses, and they help us remember. Okay. When we train ourselves to do something, all we do is program our synapses, and synapses are like memories. And for the longest times, another use case for memories were to just mimic synapses. So basically, whatever neural network learning we do, we store them in memory. And those memories are our mimic to biological synapse. Does that make sense? But now, when you use a conventional memory, like say a SRAM or a DRAM as a synapse, that will only give you 0 and 1. But our brain is not digital like this. We don't just deal with ones and zeros. We're not robots. We deal with analog signals all the time. So if there is a memory that gives you a gradual change instead of a dramatic stepwise change, will that be good or bad? What do you think? I guess I made you more confused, did I? So imagine like a phase change memory, you are gradually switching from low resistance to high resistance or back. Instead of just doing it in random steps, you're doing it gradually. That's more bioplausible. You know what I mean? That's more close to the biological synapse. So these phase change memories are used to mimic biological synapses in neuromorphic hardware, which, I haven't covered this, but I'm sure some of you have idea about what that is, or you could look it up. I'm happy to talk about it later on. But notice this characteristics here. This is resistance. This is programming power. Or in other words, this basically hides the current level here. The more power, more current you provide. Okay. Just use whatever data the papers provide, right? They decided to provide the power instead of current. So I'm showing you the power instead of current. But the point is, notice the resistance can gradually change, reduce, or increase. See the gradual, part here. If you used any other type of memory, like a DRAM, for example, you would have switched from high to low and high. So it would be like sharp, super robotic. But phase change memory, and there are some other memories out there, allows you to switch really nice and smooth. That means it's more analog because of the way things change here in phase change memory. Does that make sense to you? Okay. That's why it's a good synapse. Some design trends. Obviously, we care about retention. I told you that we care about how long it can hold on to the stored data, right? So apparently, this is the 10-year mark. This is the 10-year mark, folks. And we always care about retention at a given temperature. 110 degrees centigrade is a useful temperature that we often deal with because this is considered to be the chip operating temperature. We don't consider that the chip is operating at room temperature, despite it being at the room temperature. Because when the chips work, they generate heat inside them. It's local heating. So the temperature increases. Typically, the number is around 110 degrees centigrade, taken from a paper, by the way. So apparently, it looks like you could hit the 10-year mark, 10-year retention mark, which is a very big deal for phase change memory. So phase change memories give you good retention. Does it make sense? Okay. Or here, oh, by the way, you guys didn't ask me any questions, by the way. What is in the x-axis? So basically, notice it's 1 over kt. So the If you go towards left, what happens? Temperature increases or decreases? Tell me. If I go left on this axis, which is 1 over kT, does that represent lower temperature or higher temperature? Do you guys all agree? If T is higher, 1 over kT will be lower, so you will be going left. So the left portion represents higher temperature. So if you go to even higher temperature, your retention falls. Yeah, isn't that understandable? You know, at higher temperature, that will degrade, of course. Well, SRAMs will melt, right? Literally melt. And phase change memory will still be stable because their crystallization temperature, or, you know, simply because of the materials we are using, they could survive higher temperature. But their retention will degrade for sure. So that's okay. We don't care. That's why we point to this point where at 110 degree, you have 10 years of retention, which is more than enough for us. Okay. So that is, if you don't touch the data for 10 years, it will still be there. All right. This is endurance. These are the comments that I added, by the way. When they present these numbers in the paper, they don't point out what is it trying to tell you. You have to be the expert to understand this, okay? So this figure talks about retention. The other figure talks about endurance. So I hope by the time you finish this course, you'll be in a good position to go through a research paper and figure out which figure is trying to tell you what. And don't feel like I have no idea. Why am I here, okay? So these are all conventional stuff that we all know about. Endurance is how many cycles can it survive, okay? Notice this is number of cycles. 10 represents you just only switch it 10 times. 1,000 represents you can only read and write 1,000 times. And so on. Yes?
This is a reminder, sorry. The full swivel reset will split around a constant current when you're resetting the material.
Could you repeat the question? Sorry.
So, you use a constant current driver to change the material from a crystalline to amorphous and vice versa. So
right.
It's all the same current level?
Yes, exactly. So you have to set a lot of conditions identical before you actually measure these things, okay? They may not be too practical because in practical scenarios, things will change. There will be non-idealities and dissimilarity, but it is still useful information because, well, you could possibly switch from 10 raised to 10 to 10 raised to 8 in practical situation, but you still have some idea. But if this idealized situation show that you have 10 raised to 6 cycle, then you don't even pursue that technology at all, okay? So people still use this type of data, which are idealized, constant current, sure. And they often mention these details in the paper, not in the figure itself. Does that answer your question? Okay. All right. So notice the pulse width. So basically they're using a pulse like this. They're using a pulse. They're not obviously manually doing it, right? They set a pulse generator and it keeps writing the memory. And there is a, semiconductor parameter analyzer that keeps taking results and generates spreadsheet. And you just go there after a few weeks or so, take the data out and plot it and see how things are. Does that make sense? So what they're telling you is the pulse width is fixed. And, of course, the current level will also be fixed, but they haven't mentioned that here. It will be mentioned in the paper. So the point is, okay, just read this data with me. Is this good or not? Is this good news or not, folks? Is this a good memory or not? Up to 10 raised to 8 cycle, it's super stable. I like it. I mean, I would have liked it to be up to 10 raised to 9, which is okay, still reasonable. In fact, 10 raised to 10 is still reasonable. You see some degradation there, but still 10 raised to 9 is billion cycle. So you could read and write it a billion times, which is more than enough for us, I think. Does that make sense? So remember, in our modern day standard, anything less than 10 raised to 9 cycle is not acceptable. You have to have 10 raised to 9. Are you guys all with me so far? Okay. You might be wondering, okay, I could probably have a lifetime with 10 raised to 9 cycle. But imagine if you take this memory and set it in an application that works in 1 gigahertz. So something switches at 1 gigahertz. 1 gigahertz means, what is the time period? 1 nanosecond. Frequency 1 gigahertz represents 1 nanosecond time period. You see where I'm going with it? So in 1 second, you'll exhaust its endurance. In 1 second, right? You see the point? Okay, so you like, instead of 10 raised to 9, you like to go to 10 raised to 10. That means in 10 seconds, you'll exhaust its life cycle. Okay, 10 raised to 11. In 100 seconds, which is more than a minute, you'll exhaust its life cycle. You see, it's not much. So ideally, 10 raised to 12 is something that is more practical. But 10 raised to 9 is absolutely necessary. You have to have it. Otherwise, you don't even look at it. Okay. You see, get some realistic view now. So 10 raised to 12. I remember in some of our papers, we reported 10 raised to 12. But after that, we don't even have the time to measure. Because, 10 raised to 12 and up, it will be like in years. The time will be in years. Don't get it? Okay, just go home and calculate how many seconds would be in a year, and then express it in 10 raised to something, and tell me what is the number. Is it 10 raised to 6, 10 raised to 7, 10 raised to 5? What is it? Okay, just look it up and let me know next time. All right. Well, another quick thing. This is nothing new. As we are progressing in technology, I mean, we have seen it many times, so I don't have to tell you over and over again. Things are getting smaller. Flash memories, NAND and NOR, both are getting smaller. Similarly, phase change memory is also getting smaller. I don't have to tell you that. You already know it. But this paper tried to portray that phase change memory. Do you see that? Can you comment on what I'm trying to show you here? Basically, for a cell size, it took more time to scale. See that? Well, there were some challenges, but eventually it caught up here. It eventually caught up. And I don't want to talk about those challenges because they have been covered already, but covered in a way that they have been overcome already. So no point. This is like integration challenge, like our IBM colleague mentioned. Like there are some fabrication level challenges that people suffer with for a while. And at that time, 2013, that was a big issue for phase change memory. But now we have solved it. We don't care. Now you can scale it indefinitely. It's okay. It's not a big deal. Oh, the next one, reset current. Why do we care about the current level? Because they are related to the read-write energy. If you need higher current to set or reset a phase change memory, you'll be using up more energy to read or write, right? So if we could switch something, just imagine a magic material that switches with really low current, that would be nice, don't you think? So we love to have lower reset current and also lower contact area, because if you could reduce so this is a contact, this is another contact. In between, you have phase change memory. So no matter how small the phase change memory is, if the contacts are not small, then you don't really scale down. Am I making sense? And you might be wondering, okay, why don't we just make them indefinitely small? Because they have to provide enough current. If you make something narrower, if you reduce the area of something, what happens there? Its resistance increases. So its ability to provide or pump current reduces. Okay. So oftentimes we have to use bigger contact to pump current inside a phase change memory that is smaller than the contacts themselves. Am I making you confused? I could have just skipped these slides, by the way. I didn't mean to confuse you. These are additional information about phase change memory that people care about. But don't feel lost. I mean, if you're lost, ask me questions. Let me repeat that again. So in a phase change memory, since you have to pump current, it's all about pumping current. You have to also look at the contacts that are responsible to provide this current to the phase change memory. It's not just the material that melts. It's also the material that provides the current to melt the other one. I mean, if the contact itself melts down while trying to melt the phase change memory, it's not going to be any good, right? So to avoid that, we have to co-design the interconnects as well as phase change memory. What this data shows you is that, if you could get to lower reset current with lower contact area as well. So which is a good news, by the way. So people were excited about it. I guess all good so far. So if you reduce your contact area, you can still get to like lower reset current. If it were like this, imagine if the data was like this. Let me show you. If you reduce your contact area, your reset current will be higher. That means it's bad news. Or in this corner, This is bad in like two ways. Number one, reset current is high, contact area is high. So you don't like this area. Okay. So these are all experimental data and people showed that this is possible. So this is good news. Okay. So, and this is the final slide of this lecture and it's not new. Have we covered crosspoint before? So this is the future for phase change memory. People have been trying to get rid of the transistor for all the memories that you can think of. STT-MRAM, memristors, they're getting rid of transistors everywhere. Phase change memory is not exceptional. Okay, these blue ones are phase change memory, and the yellow one are the selectors that we spoke about. Right, we discussed this in the class, and I will discuss much more about the selectors in one of the last lectures. Literally the last lecture of this course, and that will be based on the most cutting edge selector stuff. So, anyways, why am I keeping it for the last? Because this is the cutting edge. It's like taking you to the next gen, right? That's why. So these selectors are in series with the phase change memory in cross-point array. The one additional information that I want to tell you is there is an extra vision. This is conventional crossbar. What is the difference between the figure on the right and the left? Can anybody quickly notice? Very simple point here. Just focus on this zone. This zone and the one on the left are identical. They're basically same. But the only difference here is there is an extra level. It's like a two-storied crossbar. So people, these are called stacked crossbar. So people are exploring this idea with phase change memory specifically to stack them on top of each other. Okay, this is something unique to phase change memory, which is possible to do because of the type of material we use for phase change memory. Okay, not possible for most other type of memories. So this is another promising direction that people are exploring. It's not available yet. So no more, like not a lot of excitement, but people are exploring this. All right, thank you. So that brings us to the conclusion of phase change memory and also to whatever we care about for our midterm.